Let's talk about heat loss and gain. So here's your to think about question. What part of the house allows the most heat gain in the summer or heat loss in the winter? That is something you're going to find the answer to when you do the project. So be thinking about that. When you see a little pencil icon here, that is your indication that you should definitely write this down in your engineering notebook for heat gain loss. So, first is thermal conduction. That is a process of heat transfer through a solid by transmitting kinetic energy from one molecule to the next. Essentially, that just happens when two things are touching. These things are touching. Thermal convection is heat transmission by the circulation of a liquid or a gas. That would be like air transmitting heat in some way. And then there's radiant heat. That's energy radiated or transmitted as rays, waves, or in the form of particles. So if you had a fireplace or a wood stove and it was just getting warm, it would radiate heat. Or in this case, if you have a nuclear reactor in your house, probably a bad idea. So let's look at a scenario. Heat escapes through walls and openings when the temperature outside is lower than the temperature inside. This happens in winter. We do not transmit cold, we transmit heat. So in this case, heat is moving out, but in the summer, heat moves in. We want to prevent that, so we use things like insulation. Heat loss occurs through the building structure, including the walls, windows, doors, and roof. These are all ways that heat leaves a structure. The structure requires additional heating due to the heat loss and incoming infiltrating air. So we have to add additional heat inside a building in the winter because it's cold and all that heat goes through the walls and windows and roof. So usually you add like a furnace or something like that. In the summer, it's the opposite. The heat actually goes into the building because it's really hot outside. That's referred to as heat gain. And we don't want that. We want our inside to be cool for us. So we'll put an air conditioner in there to make the inside cooler. A British thermal unit, or BTU, is the unit of energy used in the US. And here's your definition. We don't have to write this down, there's no pencil icon here. But it's the amount of heat required to raise the temperature of 1 pound of water by 1 degree. Kind of an insane type measurement, but that's how we used to as BTUs. And we actually will buy furnaces and air conditioners that have thousands or tens of thousands of BTU capacity for heating or cooling. So in the summer, you have solar heat gain through walls, windows, doors, and roof. And you also have cold mass heat gain from stuff like computers, coffee makers. In the engineering classroom, there's a bunch of computers. There's one coffee maker in our office. So it's really, really warm. Lighting also has heat gain. Now we have less of it now with fluorescent lights and LED lights. We used to have a lot more of it with the standard um, incandescent lights that we use with light bulbs because they were really warm. Occupants also add heat. You are hot. You're like a little furnace, and you produce as much as 250 BTU per occupant, or 700 if you're running around. So if you're at your computer and you're bouncing around all over the place, you're going to add a lot more heat than if you're just like chill typing and listening. So relax. All right, you're making the room too warm. 40,000 BTU per hour would heat the engineering room. So that'd be a lot of people jumping around. But we have external heat sources like a furnace. How many people would that take? If you do a little bit of math there, you can figure out 40,000 divided by the 250. That's how many people we need to actually heat the room just sitting there working. Fahrenheit is a common temperature used by engineers for heating, ventilation, and air conditioning. That's referred to as HVAC. So we may refer to it as that later on in the future. HVAC, again, heating, ventilation, air conditioning. So I don't have a pencil icon there, but if you're interested in this, in civil engineering in general, that's something you might want to just make a really quick note of because we do refer to these things as HVAC later on. BTUs per hour is a way of measuring the heating power, like a furnace or a grill. Tells you how many BTU per hour it can produce. And this one you do need to make a note of. And that's the second part here. The first one says a watt is approximately that. So we have a way to convert. But 12,000 BTU per hour is referred to as a ton, which is so dumb because it's 12,000. But that's just how we do things in the English measurement system. So I want you to write that down, that 12,000 BTU per hour is a ton. And when you purchase air conditioners, you always purchase by the ton or the half ton. So if you need 5,000 BTU per hour, you have to round that up to 6,000, which is a half ton. That's how we would do that. If you need 12,000 BTU hour, then you have 1 ton. So we're just going to be doing our measurements. We divide by 12,000 and then we round up to the nearest half unit. So half ton, 1 ton, one and a half, two, etc. Next thing to write down, what is R value? R value is the measurement of thermal resistance used. and it indicates the effectiveness of insulation. So we get some crazy units here. I'm not concerned that you have these units written down. So we don't need that. I want you to write the definition. The other thing you need to know is U value. U value is the coefficient of heat conductivity. We use this in our equation. This is the measure of the flow of transmittance through a material. So we have a couple definitions here. We're going to explain how you use these. Mainly, we need to know the relationship that when you buy something from Home Depot or Lowe's or wherever, and it has a certain insulative value, they always write in the package, this is the R value. That's thermal resistance. But to do calculations, we use coefficient of heat conductivity. We use U. So to convert from one to the other, R equals 1 over U, or, so write that down, or U equals 1 over R. It's the same relationship. U equals 1 over R equals 1 over U. You should write both of those down. In order to calculate how much heat in BTU per hour we need, this is your equation. So you're going to write this down also. Q, or Q prime, they call it Q prime, equals A times U times delta T. We talked about U in the last slide. That is a coefficient of heat conductivity. It's also 1 over R. A is the area of the wall or the area of the roof or whatever. And delta T, that's the difference in temperature outside between what do you want it to be inside? What's your ideal internal temperature? So here would be an example. So you're going to draw this in your notebook as I walk you through this. Draw this little wall. You don't have to draw it isometric. Just draw a little rectangle. Dimension it out 8 feet tall, 12 feet long. Your area is 96 square feet. Pause this. Make sure you draw that sketch. And let's move on. Now we have to calculate the R value of the wall. The R value is composed of all the different layers that make up the wall. So if you remember our framing, if you have siding on the outside, that's this little piece here. So siding is 1.05 R value for that piece of plywood there. Sometimes it just gives it to you as a solid number. It doesn't matter how thick it is. It's just 1.05. So we say 1.05 plus the R value of the insulation that goes in the wall. I get that our wall was made with studs, but remember there was an air gap in between there. That air gap is where we put insulation. Insulation is measured by the inch. So every inch of insulation is 3.14 per inch times 3.5 inches gives you an R value of 11 for the insulation. And then next we have drywall. We have a 1/2 inch drywall or gypsum wallboard. And that is 1.36 per inch. I only have a 1/2 inch of that. So a half times that is 0.68. And then there's an internal air film that sometimes we're going to include. So you have to read your design specs to see if you do that. And in this case, I'm adding another 0.68. So if I add all these together, 1, 11, 0.68, and 0.68, then I end up with 13.41. So that gives you your total R value. Now we need to convert to U. So U is 1 over R, so U equals 0.074. Don't round this up. It's not 0.075 or 0.1 or whatever. Just leave it 0.074. We get our temperature data using the National Oceanic and Atmospheric Administration. NOAA is the collector for this, and that gives us local weather data. So what we're doing is we're looking for what is the percent chance that the temperature is within essentially 99% of the days. So in this case, there's a lot of information on here. Just go with me here. So we want in the summer, if it says 89, then that's saying that 99% of the days are going to be 89 degrees or cooler. There is going to be a 1% chance it's going to be warmer than that. But we can't design for infinity. We have to design for range. So we're going to say we want to design for like 95% of the days. In this case, we've circled a 1% occurrence that it is greater than 89. In here, it's a 1% occurrence that it is less than 3 degrees. They're writing it as a 99% occurrence that it is greater than 3 degrees. That's what that means. So if it gets colder than that, fine, you put a sweatshirt on because you're not going to be able to heat your house very well. That's sort of what that means. So we're going to find a table that gives us those values. And what we want, we're going to say we're designing for the inside to be 68. This would be like in the winter. That's kind of chilly, but that's what we're going to design for. When the outside temperature is 3 degrees and we go back and we can see that is our low. So that is our winter. From 3 to 68 is 65. If we design for summer, it's 89 to 68, and 89 to 68 is 21 degrees. So that would be your temperature differential. So we're going to do it for the winter value. We have 68 degrees minus 3 is the cold, and we have a 65-degree temperature differential. That was the area of our wall. That was our U value. We multiply them all together. We get 462 BTUs per hour. That's how much heat we need to produce. So we need a furnace that's going to produce that much. That's how we solve that. Now that's just one wall. So you would do all the walls, you would do the roof, you would add up all those R values, those Q values, and figure out how many total BTU per hour we need. And that's how big of a furnace you buy. So you're going to need to do that for your shed right here that we're designing. And you're going to have to figure out the areas of the walls so that you can use that for your area calculation right here. How in the world would you find the area of this wall? Because it looks to me like there's two shapes here, a rectangle, oh, and then a triangle at the top. So rectangle, not so hard. You have 12 feet on the bottom, 8 feet tall, 12 by 8 is a number, 96. But then we have this little triangle part at the top. That would be assuming that we have rafters in here and we're insulating all the way up into these rafters. And we have an open area here that we need to insulate this triangular part of this wall also. So we need to find the height of this triangle. Well, that's going to be the remainder. If it's 8 feet up to this line, then it's 2 feet, 4.5 inches up here. So we're going to have to convert 4.5 inches into feet. So 4.5 divided by 12 inches in a foot gives me 2 point something feet. So you can get your calculator and you can figure out what 4.5 inches is into feet. That's the height of this triangle. And we know the width is 12. And you have geometry skills that tell you if you know the height and the width of a triangle, you can find the area. So that's how you find the area of that triangular wall part. And then we would add that to the rectangular wall part of 96 square feet. You're also going to figure out the areas of all the doors and all those pieces, and that will be part of what your work is. Last thing you're going to need to do is figure out how to find the area of the roof. So you're going to need to find this slant right here, whatever that slant length is. So that looks like a Pythagorean theorem problem. If we know this leg of the triangle and we know the height of the triangle, we can find the hypotenuse of the triangle. And that will give you the edge of the roof times the whole length of the roof. So we need to know how long this shed is. So we can work through that problem. Since you're watching this video, if you need some help with that, let me know and I'll help you. But that is it for this lesson. The next thing that you're going to do is you're going to be in the assignment and you're going to open up this transmission load worksheet right here. And that's where you're going to enter all of the R values for all the different walls and the roof and the doors and the windows, the area for all of them, and the change in temperatures. And how do you find all the change in temperatures? You go up to this here, average Denver temperatures. I'm going to click this document and it gives me some design specs that say use 97%, 97.5 for winter, 2.5 for summer. So we go down to where Denver is and it's here. I'm going to look at Alamosa. Alamosa says, well, a bunch of numbers here. I got to make sure I'm reading them correctly. 97.5% for winter. We're going to go dry bulb, I believe. Let's see. Yep, dry bulb. We're going to go dry bulb summer. So these two columns for Alamosa is -16 and 82. I want you to do it for Denver though, so make sure you use the Denver numbers. We have a couple numbers here and we need to figure out what do we want for the internal temperature. It says 68 degrees. So you'll have to subtract to find the change in temperature for summer and for winter. So as you're going through this, make sure you take a note of your door areas, your window areas, how many windows you have, etc. And you can calculate all of those different values and put them into your table. And there's a couple of questions, 1, 2, 3 different questions you'll answer in these boxes when you're done. And then you can share it with me. Let me know if you have any questions and I'll come help you out. Good luck.